So I've got a cool little circuit here, and when I stick an LED in these sides, boop, it turns on. But you didn't know that you could use modeling clay to make electric circuits, but if you use the kids' kind that has salt in it, it totally works. Now, stick another LED in, it lights up, just as bright. Another LED keeps working. But if I hook them up in a line, that is in series instead of in parallel, they get a lot more dim. Why is that?
Hey, I'm Dianna Cowern, and welcome to lesson 19 of Dianna's intro physics review class. This is actually the final lesson in this series. Today's theme is electricity, because that's the topic of today's lesson. Today we're going to explain that strange light bulb dimming we saw at the start of this video with two new ideas, voltage and resistance. Okay, so it's your birthday and your friends just bought you this epic electricity wand that makes metallic shapes seemingly magically dance in the air. And you know how this works from the last lesson because charges are building up on the wand and the same charges built up on the metal thing so they repel each other. Cool. So this wand required two AA 1.5 volt batteries. Did it come with them? No. But now is a great time to stop and think. What is a battery? And what does it mean to have 1.5 volts or 9 volts? How does a battery work? Let's build one on paper. So the simplest battery that I know is the one that we saw last time. It looks like this. This is the parallel plate capacitor that we described in the last lesson. So you know this already. We charged it up with separated charges. We've got positive on the top, negative on the bottom. So it's two conducting plates with charges on them. This is the simplest battery I know of. And we know from the last time that there is a constant electric field between the two plates going from the positive to the negative. That's our electric field E. And this is the simple setup we're going to use to develop our new tools for today. So think about what happens if I put an electron in here, a free electron, and I put it near the negative side. Is it going to feel a force? Yes. It's a charge in a non-zero electric field, so it's going to feel force which way? Negative charge is over here pushing, positive charge is over here pulling, so it's going to go this way. So electric field exerts a force on the charge, and it's going to accelerate quickly across the capacitor. Now, moving charges around in electric fields is a lot like lifting weights in gravitational fields. If we took out our little nano tweezers, if we push the electron in the field toward the negative side, we would feel some pushback, like lifting weights in the air. You have to do some work because you are force times distancing in physics terms. Force here is gravity, force here is the electromagnetic force. And just like you store gravitational potential energy by getting swole in gravitational fields and lifting the weights up in the air, you store electric potential energy in electric fields by pushing charges around in electric fields, specifically the way they don't want to go. So we're going to get to the equations to describe all of this in a bit. And we're going to come back to our electric potential energy, or PE. Well, it is like a little E, so you know it's electric potential energy, one of the new concepts for today. And that is what a battery fundamentally is. It's a device for storing electric potential energy. But the fields in this battery or this battery don't look like this. They're not coming from simple two-plate capacitors like this. They're actually generated by the electric potential energy difference between materials like copper and zinc. So that means you could stick copper and zinc into a lemon and that makes a battery. There it is. Because the zinc and the copper then change their chemical state once you connect them with a wire and complete the circuit, the loop, which allows electrons to flow through the wire connected to the metals. So the lemon itself doesn't release the energy or provide the energy. It's just providing an environment where the metals can provide the energy. And once you let electrons flow between the metals, you're decreasing the electric potential energy, and that is simply what a battery does. I highly recommend that DIY project. I did it for the first time this year. It's really fun. And also, some people think that when you use a battery, you use it up. Like you use up the materials and maybe it gets lighter. But think about your phone. Is it lighter when the battery is dead? Doesn't seem to be. In a battery, all the materials are still there once it's discharged. You've just moved some charges around. So the mass is almost exactly the same as at the beginning. I said almost because there's a negligible bit of mass loss because of E equals mc squared, but that's beyond this course, although it is cool. but all of the atoms, all the materials are still there. So anyways, there are fancier batteries than these ones, like the batteries in your electric car that are made with more exotic materials, like silicon coated with an elastic ion conducting polymer and impregnated with lithium, but they rely on the same principle as these batteries. An electric potential energy difference between the metals. Cool. That's how a battery works. Okay, so build a battery. You've got a way to make electrons move. But what is this voltage business? 9 volts? 1.5 volts? Okay, so I'm going to try to explain this using a gravitational analogy. So with a gravitational field, if I lift this dumbbell up, I've got some gravitational potential energy now. So even if I don't lift up a dumbbell, I still have some potential for energy. I still have a gravitational field. And the same is true here. I can push these charges across and store some electric potential energy, but even without the charges moving around or pushing them around, I still have the potential to get some energy or to do work and get some stored electric potential energy. Now, what if I want to quantify that potential for energy? Not the potential energy, but the potential for getting some energy. Well, in a gravitational field, I could say, okay, here's my potential energy, and I just divide out the mass. So then I have a number. Okay, let me write that down. So I've got gravitational potential energy is mgh. If I just divide out the mass, I get gh. But why would I want this number, this gravitational potential? If you want to calculate how much energy it would take to escape Earth's gravity in a rocket, given a mass. So you could take gh and multiply it by the mass of your rocket, and that tells you how much energy you need. I can do the same thing with my battery. Same concept. The electric potential for energy is the number, the quantity that tells me how much energy I would get if I multiplied not by mass, but by the amount of charge that I have. I can find some number where I take my electric potential energy, I would divide by my charge this time instead of mass. I should have written a little delta, and I get the potential for energy. If I just multiply my charge, like maybe it's just the charge of 1 electron, or maybe it's the charge of 10,000 electrons, then I get out the amount of energy I stored. So this is what I use to quantify the potential for energy. This is called voltage. Voltage V. It's the potential energy per charge. So this over here is its own thing. So we know that we get a potential for energy from here to here, but what voltage is just generalizing that difference in energy for any unit of charge. So you could multiply that number, that voltage quantity, by charge and get out the energy. Now, how do you change voltage in a battery? Well, in a battery like this one, you can change the type of material, the dimensions, the size of it, the construct, and so forth, and that'll determine your voltage, your electric potential difference. So then, does a 9-volt battery have a lot more energy than a 1.5-volt battery? Not necessarily, because it's the energy per charge. That's what the voltage is. Okay, so all these batteries in series, I now have, imagine they're all connected. I've got 1.5 volts times 10, so I've got 15 volts now from here to here. That's a potential difference of 15 volts. But what if instead I line them up like this and connected them all across this side instead of plus to minus, it's all plus to plus on this side and minus to minus. And I connected all these wires to one side of my circuit and all these wires to my other side of my circuit, I would end up with still just a 1.5 volt drop. So same batteries, same amount of energy, but very different voltages. In fact, 10 times different. And I could use 1,000,000 of these batteries and connect them like this with all the wires on one side, and I would still only have 1.5 volts, unless I line them up like this. Then for 1,000,000, I'd have 1.5 million volts, which would be insane. You could have a 1.5 volt battery that can give its energy to a bunch more charges, but the energy per charge is going to be lower than the 9-volt battery. This is a bit different than gravity because we don't ever run out of gravitational potential. There's no gravity battery that runs out, but that is the case with batteries. Okay, cool. So batteries store electric potential energy, and we can quantify that per unit charge with their voltage. And we can use this potential energy to power our phones and our cars and our laptops. And you probably have noticed that sometimes these toys get hot. Why is that? Well, we have to think about our next 2 big ideas. First, what is current? So batteries make electrons move, we saw that, and moving electrons, that's current. As simple as that. Current is the rate of charges, so it could be electrons or other protons or whatever, but it is the rate of charges flowing through something. And that medium could be metal, it could be air, like this singing Tesla coil made by the band Architect. So normally charges don't freely flow through air like this, but if you make a super high voltage, like in a lightning storm, charges flow as a strong electrical current, because that's what lightning is, it's just charges flowing through air, and then obviously creating some light as they go. Now, in most of our devices, the medium that current is flowing through is usually metal, like the metal wires and cables, because metals, unlike air, are really good at letting the current flow. So the second idea is why electrons flow more easily through some materials and not others, and why that current makes things hot. So electrons, typically in most materials, don't flow perfectly efficiently. There's always at least some interaction between the electrons and the atoms in the medium because they're flowing through and they're bumping into the atoms and jostling them around, passing off some of their kinetic energy to the medium. And that's why the material heats up. It's gaining some of that kinetic energy at the atomic and molecular level. So the metal filament in your light bulb actually uses this principle. It heats up because electrons are flowing through the filament, jostling the metal atoms in it around and getting them so hot that they reach glowing hot temperatures. And that's how incandescent light bulbs work. Fluorescent light bulbs are different. So as you might guess, those interactions that cause the heat also have the effect of resisting the flow of charge. Because electrons are bumping into things, it slows them down. It resists the flow. And that's what we call resistance to the current. So materials that allow electrons to flow more freely have lower resistance. So metal has a lower resistance to current, wood has a higher resistance to current, some ceramics have low resistance to current. Actually, fun fact, resistance in a material can depend on temperature. So for some materials, if you drop the temperature low enough, the resistance goes away. Not just gets small, it goes to zero. Which, now that I'm saying it, sounds impossible, but that's what we call a superconductor. And the search for materials that can be superconducting at near room temperatures is a big field in modern physics. And actually, just a couple months ago, in October 2020, the first room temperature superconductor was discovered at about 15 degrees Celsius. It's this material made of hydrogen, carbon, and sulfur, but it only works at about 2.6 million times atmospheric pressure at sea level, so it's not that useful. Okay, so that's current and resistance. So now we know the concepts that we're dealing with. Let's get to our tools, our mathematical tools to describe all of this and be able to work with it. So let's think again about pushing our charge around in the capacitor. Imagine that I push it over here and let it go. Phew, it's going to accelerate back. If I could push it back and let it go, would it keep going over and over? Yes. Phew. As long as I keep putting the work in there to give it electric potential energy to then convert into kinetic energy. But what if I push it over here really fast? Does that change how much electric potential energy it gets? Well, what's a way of figuring that out? Let's actually move all of this now. Well, energy comes from work, and work comes from a force, and the force here depends on two things you learned from last time. The force depends on the charge and the electric field. So let's translate that into the math that we can use. So energy comes from doing work, which is work, which is a force times a distance. You remember that from our work lesson. And then the force on the charge from last time is the magnitude of the electric field times the charge. So putting this all together, I get work equals my charge. I'm going to put the force in here. My charge times my electric field times my distance. That's the work I've done, and so therefore that's the potential energy that I got. My change in potential energy. Electric potential energy. So the work the field will do on the charge is the amount of charge times the magnitude of the field times the distance between the plates. That's if I move the charge the whole distance. So as long as we keep going the same distance in the field, we will get the same work and therefore the same electric potential energy that can be converted to kinetic energy, and that gives us the same speed. Just like lifting a rock up in the air 1 meter and dropping it will always hit the ground with the same speed, no matter how fast you lifted the rock. So now that we know the difference in potential energy for an electron between here and here, between the two plates, we can figure out the mathematical tool we need for voltage. It's our potential energy per charge, right? And I just figured out what my potential energy is going to be. So it's that energy per dumbbell. So we take our potential energy, which is the work we did, Q, E, D, and we divide it by charge. So the charges cancel, and I get the electric field strength times the distance. So that's the amount of potential energy available per charge. So that is our voltage. So ED, that's my voltage or my potential difference. So voltage is a measure of potential difference. And by the way, the unit of voltage is called a volt. So another way I could write what I just did is that voltage, that potential difference times Q, I'm just bringing up this Q, that's equal to my potential energy. So our next tool, current, as we said, current is the rate of charges per second. So we actually use the symbol I for current. And it is in units of coulombs per second because it's charge per time. But this is also called an ampere or an amp. So 1 ampere is 1 coulomb per second. So in a circuit, voltage is generally proportional to current, which makes sense. Higher voltage, more charges are going to flow per second. Voltage is proportional to current in a circuit. Interestingly though, increasing the current doesn't always mean increasing the speed of an individual charge, because you might think that electrons moving through a wire are zipping around, right? But no, the average speed of an electron is on the order of micrometers per second. It's just the number of charges passing through per second that typically increases. So the bigger voltage, the bigger the current it can create. Metaphorically, it's like more pent-up pressure ready to push the air. So higher pressure, more air could be pushed. Similarly with voltage, higher voltage means more charges will pass through in a second. And that's current. So lastly, we've got our tool for resistance. And we can think about what the equation might be for voltage, current, and resistance by thinking about what resistance does. So voltage is the energy per charge. Higher resistance means more of that energy is likely lost to heat. Therefore, we would get a lower current. So we define resistance as the ratio of voltage to current, because increased resistance means decreased current. And the units of resistance are volts per ampere, which is actually something called ohms. And we use the Greek letter omega to represent ohms. So if I bring back this I over here, delta V equals IR, you'll see why I'm going to do this in a second, because this is the famous Ohm's law. This is the famous equation for electrical circuits. This is like F equals MA level of importance when it comes to circuits. Voltage is current times resistance. Understanding that and using that tool is incredibly important for electricity and physics. Now, the hardest concept in all of this, I think, is voltage. So let's do a practice problem to practice thinking about voltage. Use an old school TV. Old school TVs were made where they would shoot electrons from the back of the TV to the front of the TV, which would hit this chemical that glowed. That's how it worked. Here's the back of the TV, the front of the TV. So say we shot our electrons across a potential difference, or a voltage, of 1,000 volts. So I want to know how fast the electron would be going once it accelerated across this voltage and hit the other side. Just like a falling rock problem, start with potential energy, it gets converted to kinetic energy, and we use that kinetic energy to find the velocity. So how do we find electric potential energy? Well, that was the whole point of the voltage, in my opinion. That electric potential energy will just be the voltage, which we know, times the charge of the electron. Electric potential energy, and I'm going to end up with some kinetic energy. And I'm going to use that kinetic energy to find my speed at the end, because that's ultimately what I want to know. So now we know that this electric potential energy is just going to be the voltage times the charge of the electron. And here it gets interesting. If we were doing this in a gravitational potential energy problem where we would set this potential energy equal to kinetic energy, we would have mgh equals 1/2 mv squared. We would see the m's, the masses cancel. You know what that means. Masses cancel means that all objects fall at the same rate in a gravitational field, which we know. Here I get my voltage times my charge equals 1/2 mv squared, and the mass does not cancel. So charges with different masses will end up with different velocities. That's interesting. That in a gravitational field, the speed it's going at the end does not depend on mass, but with charges it does. So we need to work out the math using the mass and the charge of the electron, and so let us plug in some numbers and work it out real quick. So I've got my voltage, which I gave you, that was the beginning of the problem, 1,000 volts times the charge of the electron, something you'd just either know or look up, which is 1.6 times 10 to the minus 19 coulombs, and that equals my 1/2 mass of the electron, same thing, I just looked it up, 9.1 times 10 to the minus 31 kilograms. and that's times my v squared. I'm solving for v squared, do all this math out, and I get v equals 1.9 times 10 to the 7 meters per second. Ta-da! Whoa, we found something like 20 million meters per second, or almost 10% of the speed of light. That is fast. So even though the energy we gave the electron was tiny, why did it go super fast? Because the mass is really tiny too. With a small mass, it's easier to accelerate you. Here's another problem, and this one is gonna help us think about why our phones get hot. And also it's gonna help us think about the power in circuits. So check out our simple circuit. I'm gonna draw a little battery here, a plus and a minus, and then it's gonna go through a little light bulb. Boop. Okay, so there's a potential energy drop between the two ends of our battery. Say this is 9 volts. So our potential energy drop, our voltage drop between this positive and negative side is 9 volts. And this drop, this potential energy drop, makes the current flow through the wire. And where does the energy go? Well, the light bulb is a big resistor, and you can literally feel the energy from the voltage drop heating up the material. You can feel it heating up the light, and then you can see the resistor is radiating the energy away as light. And if I wanted to know how long my battery is going to last, maybe how fast it's using the energy, if I wanted to know the rate of energy, it's power, it's wattage, it's our energy change, our energy over time. So that's going to be our power is our change in energy over change in time. What's our change in energy? Well, we just worked through some equations for electricity. Our change in energy is going to be our voltage delta V times Q, because remember, electric potential energy is our voltage times our charge per time. That we could rewrite as just our voltage times charge per time. That's our current. And so now we have our two basic circuit mathematical models. P equals IV, and we've got V equals IR. Power is current times voltage, and voltage is current times resistance. Mathematically, these are basically all the tools you would need. But since I'm a physicist, I like to play with my models, and so to figure out other relationships, like if I don't know the current, then I could just substitute in V over R for current, and I could get P equals V squared over R. Or if I didn't know the voltage, then I could just replace voltage here, and I would get P equals I squared R. Lots of things I can do with these two tools. And there's also really interesting intuition you can get if you just keep looking at these equations. If my current goes up, obviously I'm using more energy per time. If my voltage goes up, but I have the same current, then I'm using more power. So that tells you a little bit more about what voltage is. Just a lot of stuff in here. Really cool. So now we can use these new tools to answer our original question about the light bulbs dimming. When we hook up light bulbs in series, they got dimmer. We're going to figure out why. So I'm going to draw my circuit here. It's similar to this one, but instead I've got a battery and the voltage drop on my battery. I've got my light bulbs in series. So the current flowing across both of these light bulbs is going to be the same, because no matter what, the same number of electrons have to keep moving around the circuit, because the electrons don't just disappear. And if it's a different number of electrons across each bulb, then they're going to bunch up somewhere, and that doesn't happen. So that's one important point to always remember in situations like this. The current across both light bulbs is the same. And a second important point is that there's a voltage drop across each light bulb, because I've got this potential here, and then that voltage drops across each of these light bulbs. That is because the overall voltage does some work on each light bulb. So each light bulb sort of uses up some of that voltage, some of that stored energy. And the voltage drop across the two light bulbs adds up to the total voltage of the battery. So my voltage drop 1 plus my voltage drop 2 is the voltage of the battery. So that right there is enough to convince me why the light bulbs will get dimmer. They have to share the potential drop of the battery. But there's another way that we could have hooked up the light bulbs. We could have hooked them up parallel to each other. So what would that look like? We'd have our battery, one here, and then another one parallel to that. This is my 1, this is my 2. So the current could either go this way or it could go this way. So in this case, now the currents flowing through the light bulbs are not necessarily equal, because the electrons flowing through the circuit get split into these two paths. And the resistance of the light bulbs might not necessarily be the same. If the resistance of them is the same, is the current the same? Yes. But there's a fork in the road here. And if one path is easier to travel than the other, so easier would mean less resistance, then more charges are going to go that way. But the total current of this circuit equals the current through bulb 1 plus the current of bulb 2, since again, we're not losing electrons or they're not bunching up anywhere. So my total current is going to be current 1 plus current 2. And it works out that the voltage drop across each of the two light bulbs have to be the same. They balance out. So that's my voltage drop. It's going to be the same as the battery, and that equals the voltage drop across light bulb 1, and it's the same as the voltage drop across light bulb 2. And so again, right there, we can see that the bulbs in parallel should have the same brightness as a bulb all by itself, because each bulb sees the entire voltage of the battery. It just may happen that you use up the battery faster than if you only had one bulb connected. And that's our lesson on circuits. When they asked what you learned on YouTube today, here are your 2 key takeaways. 1, voltages are all about potential energy. And potential energy comes from the work, which is the potential difference of the voltage times the charge. And 2, Ohm's law, V equals IR. And here are the problems that we solved in the lesson, so you can go over them on your own, because that's one of the best ways to learn physics. And a short disclaimer, this series has aimed to review topics covered on the AP Physics 1 test, but just before recording it was announced that circuits, electrostatics, and waves will no longer be covered. So there's that. This is the end, y'all. I don't know who's happier, you or me. If I have one more piece of unsolicited advice, it is that I learned so much physics by making this course. And I've learned so much physics by tutoring for the last 10 years. And I'd say what I found is that when you have to teach something, you learn it incredibly well. So that's my pitch for you trying to teach something to somebody, maybe tutor people. That's how you're gonna learn the best way possible. And I wanna give a couple last shout outs to people who really deserve it. I would not have been able to do this course without my high school physics teacher, Jeff Brock, who was the lead writer on this course. And without my crew, Hope and Levi, who've been here for the whole filming, and all of the other wonderful people who worked on this course, all their wonderful names are in the credits. But I truly hope that this is not the end of your journey with physics or other science and engineering fields. In the words of past Dianna, I hope you do continue on with physics. I do hope you continue with physics. I really hope you do. And here's one final message for you from some special guests.
Hi, I'm Greg.
And I'm Mitch.
And we are ASAP Science.
Now, we spent a lot of time in university studying biology and chemistry, but honestly didn't take that many classes in physics.
And now that we're older, we're obsessed with cosmology, the expanding universe, the laws of nature, all governed by physics. So, good luck on your course, keep watching Physics Girl, and we hope you enjoy it.
See ya!